We'll go ahead and get rolling since we have a lab to do. I gave back your quizzes. The mean was something like a 48%, so it's not very good. We will do this again, not this exact one, obviously, but something that's in a similar vein. So take the time, go back and review a little bit about what we've talked about.
How much time is for this period? 10 minutes or?
So you went a little over 15 minutes in class, and originally had 10 minutes put down for this. So we'll probably do 15 minutes next time, but it'll be a similar thing. So 15 minutes, about 9 questions, and should take, if you know the content, should take you about 5 to 8 minutes to fill out probably. So go over it real quick. So number one, that is a lathe, and it's used for cylindrical machining operations or operations that can take place on some kind of section. I didn't really grade too hard on what's it used for, but make sure you know the names of some of the basic tools, otherwise it's hard to communicate with people about them. So number two, you could have said a number of things like breadboarding, printed circuit boards, wire wrap construction, perf board, Manhattan or dead bug construction. We had a decent lecture on that, and there's some pages on the website if you need to remind yourself of that. So number three, I was looking for the general flow. You didn't have to get each of the steps. The steps that we talked about where you have the physical system that is connected to a transducer in some way, then that's signal conditioned, and then that goes through an analog to digital converter, and then that's recorded somehow. So the idea was that you have a physical system and there's a transducer and you have to digitize it and then store it. That's what we were looking for. Number four is state machine. It's a programming construct that involves a fixed number of states and defined transitions between them. So it allows you to implement a complex system or a complex program relatively easily. On the back, you can go back in the class slides. We did this as one of the in-class examples. So the answer's in the class slides. Number six, we're looking for serial and parallel dimensioning. And so it depends on where you care about the dimensions, whether you want tolerances to add up, as they would with serial dimensioning, or whether you care about absolute dimensions with respect to one end of the part. So that'd be parallel dimensioning on the bottom. Seals, we talked about a wide variety. So there's O-rings, gaskets, U-cups, packed seals, Bridgman unsupported seal. There's a variety in there that any of them would have been fine. The factor of safety is when you take the maximum working condition or the maximum rated pressure or rated load of something and multiply it by this factor to get the design for pressure or load so that you have some safety built in to account for flaws in materials, welds, that kind of thing. And then Ohm's law, E equals IR, V equals IR, either's fine with units. And most people got that one just fine. Okay, any questions on the quiz? No? Okay. Like I said, it's not a ton of points. We just want to see if people are going back and try to encourage you to kind of try to internalize this, because what we're doing is building and building on this set of knowledge, and you have to have a pretty wide breadth of knowledge to do experimental apparatus work. So today there's just a few slides, and then we're going to do an activity that's on the website, hence all of the equipment here. We're going to talk about calibration. So we talked about transducers, and we said that you need to know how the volts that are coming out of the transducer relates to the physical thing that you're trying to measure, be that displacement or load or pressure, any other number of parameters. So the calibration is how we connect the output of that transducer to something in the real world. So here there's a distance sensor. This is obviously not an incredibly precise calibration, but it could be good enough for their application where they have a tape measure and they have the transducer placed at 6 inches. And then they'll know that when the transducer outputs whatever value it is now, that represents 6 inches. And they would move it to, say, 7 or 8 or 10 or 12 inches, take another reading, and build up a calibration data set. So what we do is we take the transducers through a known series of values, a series of values that we can trace to real physical units. For example, if we were calibrating a bunch of temperature sensors, we could stick them all together in this piece of metal and put it in a water bath that is precisely controlled. You know, we could mix ice in, and we know by definition we have water and ice coexisting. That's 0 degrees Celsius. Or we could boil it. We could set this, if it's a bath that we could change the temperature on, but it also has to be somehow calibrated. The idea is you have to have something that you can trust, something that is a standard. And then you take your data set, where in this case we've gone through a number of displacements on a transducer from 0 to 8 millimeters, and we've got the output voltage. We've plotted up, and luckily we're in the linear range of these sensors, so we get a very nice linear trend and we can fit a line to it. The slope of that line is the calibration factor that you're looking for, right? It's millimeters per volt, or volts per millimeter, however you want to frame that. This transducer had some issues, right? The slope looks similar, but there's some hysteresis in this curve of we went up and then we came back down, and we got some slightly different readings. So this calibration would need to be redone, and if you get the same result again, then there's probably something wrong with the transducer. Whereas here, when we went out and back down in displacement, the dots are pretty much exactly on top of each other. You can't even see them. Another thing, if you do see this, think about, did somebody do it up to here and then they go to lunch and somebody else start using the vernier scale on the way back down? You could have some kind of different bias in how you're adjusting things. And the calibration needs to be performed on a regular basis. Normally in industrial settings, you'll see these stickers on things that say when the calibration was done and when it's due. So semi-annually or annually is a pretty good number for most things. There are some instruments that you can go a few years on. But really, if you need an absolute calibration, you need to be able to trace it back to the National Institute of Standards and Technology, which is NIST. And when you get something that is certified by them or certified to be in compliance with their standards, it comes with a nice little certificate like this, and you want to hold on to that because you're using this as a transfer standard, meaning you don't have, well, we don't have in the laboratory the standard meter, or we don't have the standard kilogram. There's only one, right? But we have a transfer standard that's been calibrated against that, and we can use it as truth in the laboratory. So we're using it to transfer the information from that standard to our instruments. We've got several, for example, this is, those of you that calibrate the displacement transducer today will be using this. This is a vernier height gauge. So something like this with a certificate from NIST is going to run you about $2,000 or so. And this is a very, very accurate. You can get down to about 1/1000 of an inch positioning with this in height above the base. For load cells, I'll show you a picture of what we would normally do. What you're going to use today are these not NIST calibrated 5-pound fitness weights. All right, so here's the vernier. You'll see you have your displacement transducer affixed on a ring stand, which we've got over there. You put the core of the transducer onto that vernier right here, and then you'll move this in 1 millimeter increments, or you could do it in 0.5 millimeter increments if you wanted to, and get your calibration data set. For a load cell, we use something called a proving ring, and these have to be sent back periodically to be recalibrated. The idea is it's a large steel ring with basically a dial indicator in the center. And as you load it, it deforms slightly. And that dial indicator has been calibrated to tell you how much load has been put on the ring based on how much it has deformed. And it doesn't deform much, right? You can see, I think I may have a photo later I'll put up, but these are, I believe, 10,000 pound force increments. So even at very high loads, it doesn't deform a lot. You can get these, of course, in different ratings. So the activity is going to be to do a calibration. Here, you've got a very nice setup. You're on a table. You have a power supply and some meters and lots of room. Generally, when you're doing it in the lab or in the field, you might be like poor Brett here, who's stuck behind the biax, trying to calibrate at his new desk there. So not always the ideal situation. But the idea is the activity's online with some instructions. We're here to help you. One group, you're going to divide into two. One group is going to perform a calibration on this DC-DT. You can see the voltage on this meter. The other group is going to perform a calibration on this load cell, and you can see its output on this. I'm going to go ahead and turn this down a slight bit. Okay, so divide up into two groups. Also, don't forget, next time we're going to be putting strain gauges on things, so bring your object to strain gauge with you on Tuesday. Okay? Any questions? All right. So find your two groups.